Welcome back. Before studying ADCs, let's look briefly at an element which is common to most types of ADCs and DACs, which is operational amplifier. Fortunately, you don't need here a detailed coverage of operational amplifier to understand ADCs and DACs. We will review some basic characteristics of operational amplifier. So, what is an operational amplifier? It is a linear amplifier with two inputs. One is inverting and other is non-inverting, and one output. It has very high voltage gain, very high input impedance, and a very low output impedance. So if we configure operational amplifier as an inverting amplifier as shown in figure here, so you know that its gain is minus RF over RI, where RF is feedback resistor and Ri is input resistor. So basically the ratio of these two resistors control the voltage gain. And of course you should be familiar with the virtual ground. Here if we are grounding non-inverting input, then of course this input will be at 0 volt, and so we call it as an virtual ground. Why virtual ground? Because it's not really grounded. And so, and the other major application of operational amplifier is as a comparator. Here two voltages are applied, V in 1, V in 2, to the inputs. When these inputs differ by a very small amount, the operational amplifier is driven into one of its saturated output states, which will be either high or low depending on which input is greater. Now we are ready to study flash or simultaneous analog to digital converter. The flash method utilizes comparators that compare reference voltages with the analog input voltage. When the input voltage exceeds the reference voltage for a given comparator, a high is generated on the output of that comparator. In general, 2 raised to power n minus 1 comparators are required for conversion to an n-bit binary code. The number of bits used in an ADC is its resolution. The large number of comparators necessary for a reasonable sized binary number is a major disadvantage of this method. And a major advantage is that it provides a fast conversion time, so its name is flash because of a high throughput, and this throughput is measured in samples per second. The figure shows a 3-bit converter that uses 7 comparators 1, 2, 3, 4, 5, 6, 7. The reference voltage for each comparator is set by a resistive voltage divider circuit, this one. The output of each comparator is connected to an input of priority encoder. You can see here that these are inputs of priority encoder 0, 1, 2, 3, 4, 5, 6, 7, and the output of each comparator is connected to one of its inputs. And this priority encoder is enabled by enable pulse, enable input. The 3-bit code representing the value of the input appears on the encoder's output. So why we are using priority encoder? Because the binary code this binary code is determined by the highest order input having a high level. What do we mean by highest order input? So let's assume that input from sample and hold circuit is 5. So of course, uh, after this 5, all comparators have high output, including 5, and after this, all comparators have high output. So we have to use priority encoder so that only the highest order input having a high level would be encoded. So accuracy with which the sequence of binary codes represents the inputs of the ADC depends on two factors. The one, frequency of enabled pulses, and the second, the number of bits in the binary code. Second method is successive approximation analog to digital converter. It is one of the most widely used methods with much faster conversion time but slower than the flash method we have already studied. It has a fixed conversion time that is the same for any value of the analog input. So, for example, if input signal is, for example, 5 or more than 5, the conversion time is fixed. So, consider this block diagram. It consists of a DAC. DAC means digital to analog converter. So, we will study DACs later, but here you can just imagine that digital to analog converter will convert digital or binary numbers to analog, and a successive approximation register and a comparator. The input bits of the DAC are enabled one at a time, starting with the most significant bit. So first we will enable this MSB bit, then next, then next, and the last least significant bit. As each bit is enabled, the comparator produces an output. This comparator produces an output that indicates whether the input signal, this one, is greater or less than the output of the DAC. If the DAC output is greater than input signal, comparator output is low, causing the bit in the register to reset. If this output is less than the input signal, the one bit is retained in the register. After all the bits of DAC have been tried, the conversion cycle is complete. Let's take a specific example of 4-bit conversion. Here we have applied a constant input voltage 5.1 volts. Output of DAC depends on the magnitude of enabled input. So there are 4 inputs having magnitudes 8, 4, 2, 1. In figure A, we are going to start with MSB. That is, we make MSB is equal to 1. In this case, output of DAC, because this one is going to enable this input, so output of the DAC is 8 volt. Since 8 volt is greater than 5.1, the output of the comparator is low, causing this MSB in successive approximation register to reset to 0, which we can see here. Figure B shows second step with second bits trial, that is 2 raised to power 2. Output of DAC in this case is 4 volt, which is less than 5.1 volt. So the output of comparator, this one, switches to high, causing this bit to be retained in the SAR. So this bit is retained, and as you can see here, the MSB is 0 or reset. Figure C shows third step. In this case, output of DAC is 6 volts. Why 6 volt? Because there is a 1 on 2 raised to power bit input and 1 in 2 raised to power 1 bit. So 4 plus 2 is equals to 6. Since 6 is greater than plus 5.1, so output of comparator switches to low, causing this bit to reset to 0, which we can see in figure D. So figure D shows final step with LSP trial, and this one. Now the output of DAC is 5. Why 5? Because there is a 1 on 2 raised to power 2 bit input and 1 in this least significant bit. At this point, the binary code is in register, and you can see that its value is 0101, which is approximately the binary value of the input, that is plus 5 and plus 5.5. So this is approximately okay. So another cycle, conversion cycle begins, and this process is repeated again and again. Your assignment is section reviews 1 and 2 and example 1, and also you should try the related problems given at the end of this chapter. So if you feel difficulties, then we will discuss inshallah